All right, let's get right into it. We've all seen them, right? Those absolutely mind-blowing, iconic images of black holes from the Event Horizon Telescope. I mean, what a monumental achievement. But what if I told you that hidden inside that glowing orange ring is a clue? A really deep cosmic mystery that could totally rewrite our understanding of gravity itself. Seriously, what if this exact image, the one that was celebrated as this huge win for Einstein's theory of general relativity, is actually showing us where that theory starts to break down? That's the big question we're tackling today, and trust me, the answer is just incredible. So first, let's set up our cosmic crime scene, if you will. It all boils down to what the telescope actually saw versus what our best theories predicted it should have seen. Okay, so a quick refresher. The Event Horizon Telescope, the EHT, gave us our very first direct look at the supermassive black holes at the heart of the M87 galaxy and, of course, our own Milky Way, Sagittarius A star. And the part everyone was focused on was that dark patch in the middle, the black hole's so-called shadow. And this, right here, is where our mystery really kicks off. In the middle of that image, the EHT measured what it calls a dark depression. But here's the problem. General Relativity predicts that the shadow cast by the event horizon should be about twice as big as the dark area we're actually seeing. That's not a small rounding error. It's a huge discrepancy. And it's our first major clue. Just how big of a discrepancy are we talking about here? Well, in physics, this is measured in sigma. Think of it as a measure of how unlikely something is to be a fluke. A 5 sigma result is the gold standard for a discovery. General Relativity's prediction is off by almost 13 sigma. To put it mildly, that is a colossal inconsistency. It's a flashing neon sign that something else might be going on. So this brings us to a potential new suspect in our cosmic investigation, a challenger theory that seems to work precisely where Einstein's theory is struggling. It's called the Nexus Paradigm. So what on earth is the Nexus Paradigm? In a nutshell, it's a theory of quantum gravity. You know how Einstein saw space-time as this smooth, continuous fabric? Well, this theory imagines space-time is actually built from tiny, individual units, almost like pixels on a screen or the atoms in a crystal. This completely different way of looking at the universe leads to some very, very different predictions. And this theory makes one incredibly bold, simple, and, most importantly, testable prediction. The Nexus Paradigm, or NP for short, states that a black hole's event horizon, the point of no return, is actually half the size that general relativity predicts. Just that one change has massive implications for what a black hole should look like to us. Okay, so we have two competing theories on the table. Now for the fun part. Let's see how the Nexus Paradigm's predictions actually stack up when we put them head-to-head with the real data from the telescope. I mean, just look at this for a second. This is where it gets really wild. The predictions from the Nexus Paradigm are, well, they're stunningly accurate. For both M87 and Sagittarius A star, the theory's predictions for the dark depression, that glowing emission ring, and even the total diameter of the whole thing are a near-perfect match for what the EHT actually measured. We're not talking about just getting one thing right. It's a match across multiple distinct features. It's incredible. And this remarkable alignment, it's not just a lucky guess. The researchers ran some really rigorous statistical analysis to figure out which theory is the better fit for the evidence. And the results? Well, overwhelming is probably the only word for it. This chart just says it all. It's showing something called a chi-squared value. All you need to know is it's a measure of error, so a lower score is better. General relativity, when it tries to explain just the dark depression, gets an error score of about 168. The Nexus Paradigm score for explaining all the features? It's just 0.0062. It's not even a competition. So how confident can we be that the Nexus Paradigm is the right fit? Well, the combined analysis for both black holes shows its predictions match the data with a confidence level of 4.37 sigma. That is a 99.9972% confidence level. Again, in physics, anything over 3 sigma gets your attention, and 5 sigma is a discovery. This is a very, very strong signal that something profound is happening here. And now, for the statistical knockout punch. There's a calculation called the Bayes factor, which basically compares how likely two competing theories are. The odds favoring the Nexus Paradigm over general relativity, based on this EHT data, it's 10 to the power of 36. That is a 1 with 36 zeros after it. Statistically speaking, that number is just astronomical. And the authors of the paper, they don't mince words. They conclude that the results strongly validate the new theory's predictions and that it has serious potential as a real framework for quantum gravity. So, what does all of this mean for the future of physics? Why should you care? Let's quickly break down the big takeaways. Okay, so what are the key points to walk away with? First, the Nexus paradigm isn't just a one-trick pony. It successfully predicts 3 separate features in the black hole images. That's a huge deal. Second, and this is important, this isn't about disproving Einstein. It's about finding an even better theory that works in the one place general relativity is known to break down, the super extreme quantum environment of a black hole. On top of that, the theory also seems to explain other weird cosmic mysteries, like why some astrophysical jets are hollow. And finally, and this is the big one, this could be one of the first pieces of real, testable evidence for a working theory of quantum gravity, the absolute holy grail of modern physics. And that really leaves us with one last profound question to think about. When we look at that famous photo of a black hole, are we just looking at an amazing feat of astronomy? Or are we, maybe for the very first time, actually seeing the signature of quantum mechanics woven into the fabric of space-time itself? The evidence is incredibly compelling, and it suggests that our universe is even stranger and more wonderful than we ever dared to imagine.